His body said no. Poor guy. Let me zoom in just a little bit because some of these numbers are probably a little bit small. But it is going to get a little bit annoying as far as it's going to be hard to check problems if we're this zoomed in, because some of you are like, yay, I got them, done, move on. And some of you are like, I need to find my mistakes. So for those of you that were out of the room, just real quick, you're going to see them having plugged in, and then they're like, hey, this added together gets, whereas most of you threw the function in, I'm assuming, from yesterday. Huh? Okay. Most of you threw the function in, and so you might not be able to find your mistake if it was just here. So it could have been that you accidentally plugged in something just kind of quirky or weird in your calculator. Could have been you put the parentheses in the wrong place. Anyway, get the right answer down, and then you might not be able to find your mistake until you go back and try it again. Number 36, you see that again as they were plugging into the function. Repeatedly, you have your, okay, they're saying upper is capital. Lower is lowercase, and the only reason they're able to say upper and lower definitively is because they are having you do area under functions that are strictly increasing or strictly decreasing to where, like, from the right would all be above or from the left would all be below, so it's really clear as to which one's like a higher or which one's a lower. In this one, the higher should have been, what would the higher have been? The higher would have been the left one, right? The upper sum would have been the left, and then the lower sum would have been the right. I had to kind of look and figure out what numbers they were plugging in to make that deduction. For number 68, which I think is the last even, yeah. Number 68, the last even, let me give you guys a second. They are showing like plugging into the formulas, but the way I showed you guys the formulas was just you're doing the midpoint. So they're showing you the midpoint formula for each ith subinterval. You're using the endpoint on the right and the endpoint on the left of the little baby subinterval and averaging them. They're just showing you, hey, average to get the midpoints. But there are your midpoints. And then they went ahead and were all snazzy and they threw it into a summation, which you could have done. Didn't need to have done, but you could have. Or you could have just gone ahead and done f of 1/4 times 1/2 plus f of 3 times 1/2. Anyway, tons of decimals. To be honest, I think the graders on this one, or the answer key makers, hopefully did way more work than you did as far as like showing and writing out tons of numbers. Okay, I think I have the webcam open. Do you guys have any questions on the odds or the evens that you want some clarification on before we move on? Okay, I realize I'm a little worried that that's 2 or 3 homeworks now that we're good on. Perfectly good on. Are you sure? Okay. Section 4.3 then. It's totally fine if you are, but if you're not, please, please, please come in, get a stamp. If you're just feeling like you can't ask, or maybe like that group time was sufficient, and if it was, that's awesome. Maybe it's working better than it ever has before. Just double checking. Just double checking. All right, guys, we got to write down these notes yesterday. Once again, we're a little bit ahead, but not so much in content, just in being set up and ready to go. So I'm going to zoom in on this first page because most of you, well, some of you might not have been able to see these yesterday when you were setting it up. So let me zoom in just a little bit so we can get those formulas written down, and then we'll start looking at 4.3. Do you want to be encouraged about 4.3? You ready? Adam, we didn't do any of these notes yesterday, right? But how much of the homework on 4.3 did you do last night? More than half. Why? Because you worked real hard, studied the book, read the section, watched CalcAB videos? No. Why were you able to do it? What did I do?
He's Adam.
Yeah, I started a lot of the stuff in last section. Now, he also asked me about some of the homework sections, but at the same time, I've introduced a lot of these ideas already. We just kind of, in section 4.2, really zeroed in on rectangles. In section 4.2, we really zeroed in on rectangles and Riemann sum approximations, left, right, midpoint. But I talked about a lot more than just rectangles, left, right, midpoint. That's basically what we did, I don't know, 2 days ago for maybe 10 minutes, and then yesterday for maybe 15 minutes. But a lot of the talk yesterday was about using the calculator efficiently, reminding you of summations and how maybe it's not a huge thing on the AP, but it is a really cool tool to simplify some of your work and homework. And it's building up to this limit definition of an integral that we don't necessarily have to solve. So I'm skipping, if you guys notice in homework, I'm skipping like whole sections. Especially 4.2, there were a lot of sigmas at the beginning that I just didn't really make you do. Because the AP doesn't need you to do it. Because the AP doesn't need you to do it. But there is this underlying definition of an integral that we need to be able to recognize even though we don't need to be able to solve it the long way. Hold on. Where else this year have we seen a definition of something that we actually did need to solve? It wasn't the definition of an integral, but the definition of a derivative. Yeah, the friend card, right? What is that definition of a derivative? F prime of x equals? Nope. It's called the limit definition of a derivative. Does that help? F prime of x equals? Limit as? Close. Move it off.
X approaches 0.
Close. Move it off.
Infinity.
No, it's 0, but it's not x.
H.
Oh, H. And what does H stand for?
Delta
X. Good.
Ooh.
H stands for delta x, right? So the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. And all of those could be h's also. That means the definition of the derivative is the limit. The definition, or I should say the slope of the tangent line is the limit of the slopes of the secant lines, basically. So definition of the derivative. Did we learn how to do limits?
Yes.
Yes. Did we learn how to take a limit of a difference quotient? Yes. And then we learned all of our power rules and product rules and quotient rules and chain rules and all that stuff. Integrals, we're kind of doing it completely backwards, because didn't we learn like the power rule and the constant rule and the trig rules backwards? Didn't we learn those basic antiderivatives first? And now we're talking about like its area instead of like tangent lines, secant lines, and then definition, and then rules. We're doing rules, and then area, and now we're building into the definition. So, key idea graphically. If you see an integral, what does it represent? Who is, what is, if I'm looking at a graph, wow, really? Nothing at all? Huh. That's a first. It's usually mad, it's just not usually on. Uh-oh. You guys just get all the time, don't you? Is it solid green? Is it off? Is it red?
Now it's solid green.
Okay, we're back. Graphically. I know, so much to talk about. Come back. If we're looking at a graph, we saw yesterday a definite integral solves for the exact area from a function headed to the horizontal axis. So if I was to be trying to show this expression graphically, wouldn't I just have some arbitrary, I don't know what function f, right? Where would my a and b go on the graph if I was just to put it some arbitrary place? What are a's and b's? X's, y's, points? X's, good. So a would be the lower x limit of a region. B would be the upper x limit of a region. I would be drawing those to the curve. And remember the integral, like you guys saw in your calculator yesterday, doesn't it do the perfect shading, right? And the shading always goes from the function to the horizontal axis, towards the horizontal axis, which is sometimes below or under and sometimes above or over. So, if that's the idea of a definite integral, that perfect area towards the horizontal axis from the function, between an a and a b. Why does this down here say, hey, these definite integrals can be solved solely with geometry? And this is probably what was a little hard to see. Integrals, you guys hopefully didn't see or at least had no idea what an integral was until you got to calculus. Or at least you knew it was something covered in calculus. Why is it saying use geometry? does geometry have to do with area? Oh, what does geometry have to do with area? Well, maybe we should look at who this guy is. So who is this guy? What function am I taking the area under or between? Not 4x. 4x is the antiderivative. I know what you're trying to do. But technically, 4 is the one that's in there.
Just the line.
Just the line. What kind of line? Constant, like y equals c, the basic graph, right? But it's not y equals any c, it's y equals 4. So I have the function y equals 4. So I want you guys to take a second, and can you graph whatever you know about those two functions? Go ahead and just get the graph. And once we get the graphs, maybe you can think of, she said that the bounds indicate the x's that mark the beginning and end, the lower and upper limits of the area. Just give you guys a second, because you're going to have to do this in homework. I'm not going to be able to tell you what they all are. Who's the second guy? What have you gotten so far? Oh, come on, who's the second guy? That's y equals c, he's a straight line. This is y equals
Line should be up to
mx plus b.
a line.
A line with an intercept of 2 who has a slope of up 1 over 1, right? Down 1, left 1, down another 1, left 1, up another 1. Why am I still going with my points? Because don't I have to go to 3 anyway? And up another 1. So I have my 2 and my 3 and my 4 and my 5. Boop. Line. Okay, how about this last dude? He's the hard one. Do you know who he is? The semicircle, yeah. And this is one that if I were you and you make little different colored AP notes, they love this guy. This is a square root of r squared minus x squared, where r is the radius. So who's the radius of the circle, guys? 2. So I'm going to go ahead and go 2 to the right, 2 to the left, 2 up, 2 down. But here's the tricky part. How much of a circle is this? Not tiny. Half of a circle. Because technically, if we were to take where this comes from, which is x squared plus y squared is r squared, and this is y has been gotten by itself, you have the square root of y squared equals this, which means technically it's a plus or minus or an absolute value of y. This is only half of it. This is only the positive or the principal root, so I'm only talking about the top of the circle. I'm only talking about the top of the circle. Not the bottom. Like literally, this function does not go below. If it went below, it wouldn't be a function. It would fail the vertical line test. Okay, I need to go between 1 and 3. So wouldn't that be like a this and a this and a this-ish? Does that make sense? I'm going between 0 and 3. And then I'm going between -2 and 2. Which is not always the case. Sometimes they like to go between like 0 and 2 and do a quarter circle instead, but this is a semicircle. So guys, once you have the pictures, do you realize why it says just use geometry? Because the first one is just a what? Almost a square, not quite. The way I drew it, it looked like a square, but why is it a rectangle? Yeah, it's a 4 by 2. And so if I want to solve the definite integral, I can just say, oh, hey, it's a base of 2 times a height of 4. And it's not even like an approximate, it's an exact. Yes, it's equal to h. For the next one, letter B. This definite integral is equal to, all I need is, why am I doing 1/2 with a plus? Why is it so much more complicated? It's a triangle on top of a rectangle, so you could do it that way. Also known as a trapezoid. The trapezoid formula says, if you remember it, 1/2 base, which is the 3, times height 1 plus height 2, or some trapezoids are on their side, so it's 1/2 height plus base 1 times base 1 plus base 2. It's the average of the ones that differ times the constant, so the average is adding the 2 that are different. It goes to a height of 2 and a height of 1, 2, 3, 4, 5. So you average those differences. those different heights, I should say, the sum of those different heights, and then times that constant base. Or just do a rectangle, boop, 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 plus a triangle, boop, 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 boop. But either way, why am I being snazzy? Because I don't want to make mistakes. So I'm sticking it to the man. How about this last one? He's curved. How can I do a curved one? Yeah, what is area of a circle? And I'm doing half because it's just a semicircle, and my radius is 2. In order to check in the back of the book, we know we have to simplify, but I'm just doing the whole 6. The man, don't make a mistake. Let's pretend it's a long answer. What did we do in section 4.2? We said, okay, what if we have some sort of function? Let's do like x cubed. And we're going between something like, I don't know, 2 to 5. We want to find that area. Are we going to be in some trouble? Yes. At least we're going to be in trouble if we only know how to do it geometrically. And so, and then in section 4.2 that you guys just finished, they said, okay, what if it is curved? Well, so far all we know how to do is approximate. And so you would say, okay, to go from 2 to 5, no big deal. We have our function, our f of x. In section 4.2, they would have just given you a function. They would have said you're going between the interval 2 to 5. They would have told you how many rectangles to use. What would have been like the nicest number of rectangles to use to approximate, guys, for this one? Yeah, 3, because then you get to go by. So let's go ahead and do 6. You're welcome. What are we going to go by if we're doing 6? Halves. Did anybody of you guys, in trying to be strategic in your, let's go 1 and then 2 and then 3, and then cut each of those in half? There we go, there's 6. Each of you started doing. Did any of you start doing decimals last night because you realized maybe the calculator was easier? Yeah. If you were doing it by hand, please don't go to decimals. That's nasty as far as plugging in. But in the calculator, like, man, it's so much easier to do. What are we doing? Divided by 6. So do 2.5, then 3.5, 4.5. Then trying to think of, okay, 4/5 or 4 halves. So then 5 halves, 6 halves, 7 halves, 8 halves. I don't know. Plugging into the calculator, I think it's easier to do decimals. But if it is a non-calculated question, I would almost just stick with the fractions because it's a little bit safer. But then we would have had to, well, if we're doing it on our own, we'd say, hey, let's go from the left, or hey, let's go from the right, or hey, let's go from the middle. If you're doing that really cool sigma, let's just say we're going from the right, just because we practiced one of these from the left yesterday. When we were trying to, I think, go to 10 and 100 and 1,000, remember? We were trying to get 24.0000000 to see like how many rectangles we'd have to put in order to get the right answer with rounding. If we were doing a sigma, if we were coming from the right, question, guys, which x values would be plugging into f in order to get those heights? We're doing 6 rectangles. Our bases would be 0.5, but who would we need to be plugging into the f? From last night, just don't worry about this. Don't worry about this. Who would you be plugging in? Starting from 2.5, not from 2. Did anybody start from this side and just count backwards last night? Or did all of you guys just either start here for left, or start here for right, or start there for midpoint? Raise your hand if you always started from the left-hand side, and sometimes you started one in, and sometimes you started exactly. Who always started from the left and just always counted up? Okay. Did anybody start from the right and say like, hey, I'm going to go 2 and then, but then if it's a right, I'm going to go 5 and then? Did anybody start from the other side? Okay. That means that you didn't do homework. Okay, anyway, coming back. So, we need to start at 2.5 with the right hand because for this first subinterval, we don't use the left, we use the right. So 2.5 and then 3 and then 3.5 and then 4 and then 4.5 and then 5. What would we have to plug in my fingers, what would we have to plug in order to get, if I plug in a 1, I get 2.5. If I plug in a 2, I get 3. If I plug in a 3, I get 3.5. Okay, 2 plus, good. That's a strategy. 2 plus, we always start with A because it's 2 and then we're always adding to that. We're always adding 1 jump or 2 jumps or 3 jumps or 4 jumps. Oh, nice. 1 jump, 2 jumps, 3 jumps. Jumps of what? What are we jumping by? What are our units? 0.5. So we're doing 0.5. Now, yesterday we had to do I minus 1 because the very first one for a left doesn't add anything. But the nice thing is the right ones are actually way easier to put in because I can just say I because I start 1 away, 1 jump away from 2. So actually, even from the right, it's easier than from the left. Guys, what would I need to change if I was instead of doing 6, I was doing like 100? What would change in my sigma? Does the 2 change? No. Am I going by 0.5 still? Oh, because that would only be 6 jumps. I need 100 jumps now, so hold on. Wait a minute. What would I be going by if I was doing 100? My distance divided by the 100, which would be 0.03. So I would just take my distance, and instead of my distance being divided by 6, my distance is now divided by 100, times my distance divided by 100 instead of my distance divided by 6. Do you see the pattern? So what if I wanted, ready? What if I wanted to go to infinity? Ooh. Here's a problem. Can I plug in infinity? Is that proper to plug in infinity like in a formula? No. So if I wanted to go to infinity, I would actually need to, and BC is kind of learning this right now, I would need to just kind of attach an n for number of rectangles, and then have this out in front say, okay, he's getting bigger and bigger and bigger and bigger and bigger. Now, where else does the n go in my formula? 2 plus 3 is still my distance, but over whoever I'm splitting up, or however much I'm splitting up. Good. And then what's over here? This is the definition of 0 to 3. Is that what we're doing? Of 2 plus, nope. What's my function? Thanks, I forgot who I was even doing. And it wasn't from 0 to 3, it was from 2 to... So technically, if we were to keep going, we would go one step more, and we would do 2 plus 3 over ni cubed. 3 over n. Sigma I equals 1 to n. As n goes to infinity. Now today I might not spend tons of time on this, but I could go ahead and show you what we would do, and maybe some of you remember when we did this in pre-cal towards the end of the year. I know brains were a little fried. We were doing sequences and series. You were like common ratios and differences and all that jazz. But if we were to solve this, the big old long limit of a secant line is a tangent line, the long way of doing a derivative. If we were to do this integral the long way, what we would need, oh, come on, webcam. Smartboard was mad, webcam was mad. Okay, everybody's mad. If we were to solve this, we would need to go to a section in, oh, he's still mad. Let's try one more time. Nothing? Oh, so sad. Well, I guess we're definitely not talking about it today. I don't know. He's sad. That's what's going on. Probably my computer needs to be restarted yet again. But in the very beginning of section 4.2, there are nice little formulas about how we could take a sigma, forget it, take a sigma with i's and actually rewrite this whole bleh in terms of an actual equation, which is really similar to way back when you were doing the limit as h goes to 0 of f of x plus h minus f of x all over h. If we were actually using this to find a derivative, wouldn't you guys have to plug into a function, right? And then wouldn't you have to do some work in order to be able to take that limit? That's kind of what's right now keeping us stuck from just seeing the answer. Because the answer is the actual number of the area, not just an approximate like we did up above. The answer needs us to somehow deal with this and there's an I right now, and N is, I'm confused. We would need to actually use some pre-cal skills of breaking the sigma into a formula. So kind of like using the formula, plugging it in, breaking the sigma, using some formulas, and then we could take a limit and we could see the final answer. If I get my webcam working on Monday, we'll peek at it as to how to actually solve using a limit. But the cool thing is in homework, and specifically because of the AP, I have limited problems to where you don't necessarily need to solve this. What you need to be able to do is to match it to this notation that we're going to soon and very soon in section 4.4 learn how to do. So we're technically not yet to exactly how to solve this, even though I showed you yesterday. Or why we're able to solve it with an antiderivative. It's okay, Jared showed you a long time ago how to do it. Jared. But what I need you to do is to be able to match this up. So let me actually show you one more thing, because this is actually a little bit more detailed than even the book is going to have as far as the definition. They're going to say, okay, remember where that 3 over n came from? That 3 over n technically came from delta x, what those jumps are that we were doing, which was 5 minus 2 all over n. So they say, okay, remember, those are your delta x's, so they go a little bit farther. And they say something like, oh, okay, it's going to be 2 plus delta x. They could say a sub I. They could say a sub I if they want to be snazzy like that. And then they could have that being cubed, and then they could have times delta x sub I. That's one way of showing it, or there's another way of showing it. And the other way of showing it is instead of having n go to infinity, they might also have something called a partition going to 0. That is another way of kind of showing what's going on.
Double absolute.
Yeah, it's a double absolute value. It's kind of weird. Although in pre-cal, we saw double absolute values when we were talking about magnitudes of vectors. So it's not brand new. But, yeah, you haven't seen it very much. You haven't seen it very much. But you could have a sigma where the partitions are going to 0, and let me show you what that means. The partitions going to 0 could be something like these little delta x guys, which are the bases of our rectangles. What it's basically saying is that these little bases are going to 0, which, to be honest, is the same thing as the number of rectangles going to infinity. So either one technically gets the same idea across of us fitting in thinner and thinner and thinner and thinner and thinner rectangles in order to get better and better and better and better and better approximations. And as those bases go to 0 or the number goes to infinity, same thing. Both of these approaches are definite integrals. Now, don't worry. I just used an example and I went crazy because I've been doing that with you guys just because we're able to have a little more fun and go a little deeper. But I do have a forever card coming that will walk us through the definition of derivative. So let's keep going. Let's get a little further. A little farther? A little further. We do have trapezoids. First. And that definition is coming. Let's talk about trapezoids quickly first. Oh, I'm going the wrong direction. No wonder I'm like, whoa, back. The motion packet's coming back. Yeah, but remember, motion packet, you won't need to remember. We do have, before I do the definition of the definite integral, remember, we were just doing n equals 6. We were still approximating. We haven't made a forever card for that yet because I want to show you one more way of approximating. So, before we get to that definition, before we're going to infinity, let's pause and be like, oh, trapezoids. Trapezoids, one of the better approximation techniques along with midpoint because the trapezoid doesn't allow for as much error. It's just trickier as far as the math, and if we're going to infinity, an infinite number of trapezoids are approaching an infinite number of left or right or midpoint, they're all going to approach or converge to the exact same area. So trapezoids are good if we have to do it by hand or we want the best approximation that we can. But if we're just going to be using the limit definition, it's like, forget it. Let's do the right because it's the easiest, it's the simplest. You don't have to do this crazy area formula. But the AP does sometimes make you use trapezoids, so we have to know this area formula. So quick reminder from yesterday, remember the bases would be like delta x's, and we kind of switch height and base to make it easier on yourselves. So we would do like 1/2, technically height 1 plus height 2 times base is the order that we're going to do it. And if you remember from yesterday, those heights are function values, like f of x sub, we could do I minus 1 plus x sub I times delta x sub I. You could do it that way, times delta x sub I. This is the exact same function that we were doing all day yesterday with 9 minus x squared. So I'm going to just remind you of him really quickly, and we're going to do yet another approximation of him now using trapezoids. Still on the interval, -1 to 2. So that's what we were doing. Still doing approximation. We did left, we did right, we did midpoint yesterday. We had 22, 25, and 24.25. What would a trapezoid say? We're still going to say n equals 3. All that information is the same. I'm just reminding you what it was. But what would it look like for trapezoids? Well, trapezoids are kind of long. So I'm going to go ahead and do, if you guys don't mind, A1, A2, A3, like up and down would have room. But they all have 1/2. So that's the formula. We can put our little delta x, which is going by 1, down here at the end. Because we're just doing that n equals 3, the easiest one. But this time, instead of, in our number line, instead of going from -1 to 2, and we have our 0 and 1 in between, instead of starting with -1, or instead of starting with 2, or instead of starting with -0.5 like the midpoints did, trapezoid said, no, for any certain subinterval, I need both guys. I get to do 2 heights. Oh, I should have done an F of. That would make more sense. 2 separate heights. F of x sub I minus 1 f of x sub I. 2 heights, not one weird combined height. I get to do 2 heights, which means I get to go ahead and do f of -1 plus f of 0. And then I get to do f of 0 plus f of 1. And I get to do f of 1 plus f of 2. Unlike the rest, trapezoid uses everybody. The trapezoidal approximation uses everybody. Because it says, hey, go up at -1. Got it. Go up at 0. Got it. Go up at 1. Got it. Go up at 2. Got it. And then it says, hey, make a trapezoid. Hey, make a trapezoid. Hey, make a trapezoid. Is it perfect? No. Why? Because I have curves and this is straight. But is it stinking close? Because I have trapezoids. Now, if I was trying to use my calculator to be efficient, you guys see that I would pull my trapezoidal. You could call it T-ran, but not many people do. I'll just say A sub that. I could pull out a half from everybody, because in trapezoids, everybody has a half. They're all equally spaced. I can pull out the base of 1, because everybody has a base of 1. And then I could actually, well, wait a minute. If I pull out the halves, if I pull out the 1s, isn't it just each of these guys added together? Do you guys see any like terms if I just start adding everybody, like all together? How many f of 0s do you have? How many f of 1s do you have? Oh, I only have 1 of each of the endpoints. So technically, I could even summarize it more as long as I'm equally spaced and can pull out all the bases and all the halves. But what I just said is as long as I'm equally spaced. And the sad thing is, the AP loves to give me and give you eventually unequally spaced. At which point you wouldn't necessarily just be able to pull out and make it all look a lot nicer and simpler and neater. But if I was to go ahead and throw this into my calculator, I think I still have my 9 minus x squared in there. I would just have to go to my home screen. And we could try to make a sigma, but if you guys notice, this is a bit messier as far as getting it all down. I think I might just do my 0.5. For context, we could throw our base next. And then where do we find that nice y1 to make our lives easy? Alpha trace, there's y1. I use my -1 once. I'm going to use my 0 because it's in 2 different trapezoids. I'm going to use that twice. I'm going to use my next one, which is y1 of 1 twice, because he also has 2 trapezoids. And then I only have one of the last ones. Yeah, I think I did 2. I didn't do 2 of y of 0. Thanks, Kathleen. Wait, how do I put something in without it overriding and me having to type the rest of it all out? Being efficient with my time. Second delete. Yeah, second delete is that insert. I can just throw in that 2 and not mess everything up. There we go. 23.5. So ironically, who ended up being the best approximation yesterday? The actual was 24, if you guys remember. We had 22, 25, 24.25, and 23.5. Who was the best one? Midpoint actually beat it this time. Midpoint actually beat it this time. Because midpoint does have more error when it juts out, but then it kind of offsets it with going in. Midpoint does a little bit of both. Sometimes the trapezoidal is best, but sometimes the midpoint is best. They're both just what we call the better. We're the better ones. So, approximating integrals. Long story short, on an AP, you guys don't have to figure out which one's best. That's never going to be the question as far as estimation. They all, if a limit to infinity is taken of that region sum, they all get to the same place. It's more the AP is just going to test if you know how to do them. And so therefore, to kind of summarize what we've done, and I know it's kind of silly and it's kind of basic and yet it's still kind of important. Area equals base times height. I'm going to do height times base because that's typically what we're doing. We're doing the heights, the f ofs, and then the bases, the delta x's. Trapezoids. Area equals 1/2. I'm going to do height 1 plus height 2 times the base. You could do height 1 plus height 2 over 2 times the base. That's something that you might have seen in, like, I don't know, geometry, algebra, whenever you first started seeing trapezoids. But just quick reminders, those h's are just our f of, we can call them c sub I values if you want to be really snazzy like the book, or f of x sub I. It's basically just heights you have to plug into the function, and the I just says, like, okay, they change every time. You got to go through your number line. And then the bases are delta x sub I. It'll change it. X's. And if you're able to do this all by hand and make it yourself, then why not just take the b minus the a and divide by n for n rectangles or trapezoids for n figures? Why not? Oh man, I am so off on numbering. We haven't done one of these in. What was the forever card for our integration rules? Integration rules, I think, is the last forever card we have, isn't it? The definition, the answer is the integration rule. 31. I need to update those forever cards. Maybe I should have that done by then. Okay. So approximation. But approximation leads us to all the other stuff I was saying, which is the definition of the integral. Because if the rectangles, you don't have to write that down. As I have more and more and more and more and more rectangles, as I go to infinity, I have the actual area, and that's that definition of that definite integral. So now we're getting into basically homework help questions as far as, okay, what do we do with all this stuff that we know? This definite integral we've seen represents area. It's technically found with some crazy pre-calc formulas that we just didn't have time to look at today. But breaking down a sigma of bases times heights, or technically heights times bases, still rectangles, fitting in an infinite number of rectangles. But we're going to learn like a calculus-y way to solve this, even faster in some ways, because you guys already did antiderivatives than we did with normal derivatives. So So this whole section isn't you actually solving this by hand, it's more making connections, maybe doing some geometry, maybe sketching some areas, maybe writing some definite integrals, for this is what I would use to solve. Maybe drawing some comparisons from given information to what the integral would look like. You're just drawing conclusions or drawing, comparing, contrasting, trying to go from, well, hold on, in words. What is this guy? We can say the definite integral of f of x from x equals a to x equals b. That's technically who this guy is, the definite integral from a to b of the function f of x from x equals a to x equals b, is the limit as the number of rectangles increase to infinity of the Riemann sum approximations. And technically this is a right Riemann sum. If you want to make that connection, it's an RRAM. It doesn't have to deal with like a whole I minus 1. And the in words, guys, it's more so that you can actually just say these things properly. It's not so much memorizing word for a forever quiz. This is forever number 32. So, good news for you guys. Period 6, they're not going to get through it all. You guys, I could technically, I think, just say finish homework on Monday. I'll probably have a due Google Classroom Tuesday. I knew I'd be a little bit off. But we're only going to go through some homework helps. We're only going to go through some homework help examples before starting 4-4 on Monday. We get to the calculus, finally. The fundamental theorem that lets us solve this guy straight away with those antiderivatives that we've talked about since the beginning of chapter 4. So hang in there, kiddos.